right, so we're going to pick back up where we left off, and we were working with Roman numerals when we left off, and it's the only numeration system that I said we were actually going to do conversion with, right? And we actually last time converted from, well, we didn't actually do any conversions last time, we were about to start conversions, right? So the one we're going to do first, we're going to convert from our system, our regular, Hindu Arabic numerals, into a Roman numeral. And the numeral we're going to work with first is 1,492,000. Nope, 19 at the end. Here we go. And some things, let's just jump back here for a minute. One more back. Okay, maybe way back. These are our numerals that we worked with last time, and we talked about some additional properties that Roman numerals have. There was a subtractive property, so 4s and 9s in particular are written a little bit differently. We don't just duplicate the numerals. And then we talked about this multiplicative property. If we have numbers that are bigger than 1,000, then we can use values of bars, basically. Put a bar on top of something and multiply it by 1,000, or 2 bars on top of something and multiply it by 1,000,000. And so it avoids us having to have additional numerals. So if we're taking a look at this one that I've got here now, 1,492,019, we've got that property going on, that double bar, or those bar properties going on. So there's sort of some ambiguity on how we maybe would want to see this written, but we're going to do it the way that the Romans would have done it. That's the whole point, right? So when we take a look at this, anything that's beyond the thousands place here, it's going to have some kind of bar above it. And if I can write it, that is if there's a 1,000,000 something, do you know what 1,000,000, let's say it this way. If I looked at just the part that's in red, it's 1492, right? 1,492. If you took 1,492 and you multiplied it by 1,000, you'd get 1,492,000. You would just move the three more zeros in the end. So we're actually going to write the numeral for 1492 out and put 1 bar on top of it. Now I recognize that the millions is there, okay? But we're only going to use the double bar if it's something more than 1,000,000. That's what they would have done. If it's something more than 1,000, that's when the bar comes into play. And if it's something more than 1,000,000, and I don't mean 1,000,000 and some change, I mean like the number needs to have 2 there. If it said 2,000,000, then we could use double bars on top of things. But we don't have that here. We just have 1,000,000. Okay? So we're going to be looking first at the number 1492. So how do we get one? So again, ignore the fact that it's in the millions place. Right now we're just going to write it as though it said 1,492. How do we get the number 1,000? That's an M. How do we get the number 400? We kind of talked about that one last one. Do you remember? How do I get 400? C, yeah, the smaller one before it. So C and then D. Because C is 100 and D is 500. So put 100 and 500, that's 400. So I'm going to do CD for 400. I need 90. How do we get 90? X, C. X is 10, C is 100. Got 10 in front, 100 next, so that's 90. And then how do I get the 2? 2 I's, or 2 what look like our 1s, right? So this is the number 1,492, like Columbus sailed the ocean blue, right? Okay. So in order to write this then in the millions place, which it actually is, we need to multiply by 1,000, and the way to multiply by 1,000 is simply by putting a bar on top of what we've got so far. And then you're done. But then we have the 19 at the end, right? So if this really just said 1,492,000, this would be it. But we also need the 19 on the end. So how do I get the 10 in the 19 spot? Like this 1 right here, how do I get that 1? That's X. And then how do I get 9? IX. And notice that XIX at the end cannot be underneath that bar. Right? That would mean something different. So we've got the XIX. Okay, so that's coming from our numerals into their numerals. Right? And we're going to go the other, I'm going to go the other direction, which we're not. I guess I'm not. Oh, we did their direction, didn't we? We did that one on C above. I forgot. Yes, we went from their numerals into ours on part C. Okay. I want you to take a look at something. Have you guys seen base 10 blocks before? I think I know you guys on. right, so I'm going to draw some pictures of them, but I want you to see that they really exist in like tactile formulas, and you can hold them as well. Shows that that isn't going to be on the video because you can't see it. But so this is a digit of 1. It's like a little bitty cube, right? This is a single, what do they call it? They call it a unit, right? If you stick 10 of these together, you get 10 of them stuck together. I know it's really exciting. But this is actually something they call a long. This is representing our number 10. So this is our units position, right? This is our tens place. They place value here, folks. This right here is a 10 by 10. So how many's here? 100, and this is called flat. Okay, and so there's 100 little squares in here, and then this one right here. This is 1,000. So this is a unit square. This is a unit cube rather. So it's got not a unit cube, but a cube. It's got 10 on each side, right? So it's a cube. And then if you multiply 10 times 10 times 10, you get 1,000. This is called block. Okay. So this is sort of an imagery of our base system, right? So in our base system, we have our units. We have a long, and you do not have to draw out all 10 of the little blocks inside there. Okay. You can draw it out as just one long. That's okay. We have a flat, which looks like a giant square, not to be confused with the little bitty tiny square of the unit. Don't make me guess, right? Show me. And then the block has to show 3 dimensions. So I don't know if you guys remember how to draw in 3D, but here's how you do it. You draw a square, you draw lines back of equal length on all 3 corners, and then you attach them together, something like that. And that's my block, okay? And so what this is actually showing is it's showing the base 10 system. So this is my unit, it's worth 1. This is my tens place, and for us that's worth 10. This is my hundreds place, and that's worth 100, or sometimes we would write that as 10 squared. And then this would be my block. I'm sorry, I'm not using that language. This would be my thousands place. And this would be 1,000 or 10 cubed. So this is what we already call the unit up here, right? So they already match. A long is a 10. This is a unit. A hundreds place is or a hundreds placeholder is a flat, and then a thousands place is a block. And I bring this up because I want you to know there's absolutely nothing special about the base 10 system in doing this. And to show you that that's the case, I've brought some of these puppies in another system. Okay, so no matter what system you're working in, we're working in base 10. The unit is 1. These have got little round ones in here, like so it's still 1. But this is base 3 because a long in base 3 has how many pieces stuck together do you suppose? 3, right? There's 3 of them stuck together. And then if I do a flat, I've got 3 by 3, which means how many are stuck here? 9. So in base 3, this would be my hundreds place, my third place from the left, from the right. Third place from the right, which direction's right. And it would be worth 9. And this is my block. Well, that's flat, I think that's the right word. And this is my block. So it's 3 by 3 by 3, so how many of them are each those in there are stuck together here? There are 27. So this is what it means to talk about other bases. The imagery is still the same. I still have the individual piece, a long piece, a flat piece, and block. Okay? So let's take a look. And again, this is a contemporary math something if you've had a contemporary math that you've seen before, but maybe not quite from this perspective. You have other base systems. Okay? Base 3 is the one that I just mentioned. So in base 3, what I want us to first consider is how many numbers, or what are, not numbers, but what are our numerals in base 3? Okay? So in base 10, what are our numerals? We did not do this last time. 0 through 9, right? So what do you suppose are our numerals in base 3? 0 through 2. Base 3 has 3 numerals, but 3 is not one of them. just like base 10 has 10 numerals, and 10 is not a numeral in base 10. What do you suppose happens after I run out of digits? Okay, so like, what would I stick together, Lauren? 1, 0. Because that's what I do in base 10, right? I run out of numerals. 9, that's my last one. What do I do next? Well, I use another place value, don't I? I put a 1 here, and I make it back to 0 over here. Right, what comes after 9? 10, 1, 0. What comes after 2 in base 3? Quote unquote 10 is a 10, it's 1, 0. What would be after 1, 0? 1, 1, and then 1, 2. And then what? 2, 0. And we would continue. So everything works just like base 10, it's just that we have to stop at 2. Right? We can't go beyond the numeral 2 when we're writing out our numbers. We have to move on to the next value one place over. What about base 7? What are my numerals going to be in base 7? 0 through 6. And then after 6, what's going to happen? 1, 0. 1, 1. Okay, I'm going to get it to the chase. We're going to get to 1, 6, right? And then we're going to become 2, 0. Keep going. Okay, now base 12 is different. What's different about base 12 than 3 or 6 so far? It's higher than base 10, isn't it? The others, all I had to do was just drop off the extra numerals I wasn't going to use. In order to do base 12, I need more numerals than I already have, don't I? So I'm going to have all the same numerals as before. I'm going to go from 0 to 9. In contemporary math, you may have done something like A-B next, or A-B-C, or whatever, you added letters alphabetical order. And that's actually my preference, but your book doesn't do that. So what your book does is for the digit that has value 10, it uses a T. And for the value 11, it uses an E. And as you can imagine, if you went up to 12, which we don't here, because this is base 12, there is no 12 digit. But if we were at base 13 with a 12 digit, we run into a problem with this approach, right? Can't any longer use the letter of the word, right? Can't use T again. So as luck would have it, your book doesn't go any higher than 12, so it doesn't matter, right? So T is for 10 and E is for 11. So what would happen after the E? I'd have 1, 0. And I'd continue that up till 1, 9. What would happen after 1, 9? It would be 1T. And then 1E, and then I know some of you are already telling me 2 zeros next, and it would be after the 1T, 1E. Okay? So we're going to work in this numeral system, and the first thing we're going to do is just like we did with the Babylonians and the Mayans and so forth, is we're going to take a numeral in this weird system, and we're going to find the digit right before it and right after it. And again, the whole point in asking the question is that probably one of them is easy to find, and one of them looks a little different, okay? So looking at the digit 1, 4, base 5, and we do not read that as 14. Because even when I say the word 14, 14 tells you base 10 and not in base 10. So we are going to say 1, 4, base 5, okay? So what comes before 1, 4 in base 5? 1, 3, okay? So this is the 1, 3 comes before it. And then I'm going to write 1, 4 in just so that we're writing in order and there's no sort of ambiguity what I'm doing. What would come after 1, 4 in base 5? 2, 0. Why isn't it 1, 5? Can't go up to 5 in base 5, right? So I have to increase the digit to the left, and I decrease the digit on the right-hand side to a 0. And every time I write this, I need to write that I'm in base 5. Because we don't write bases next to our numbers when we generally write them, right? If you do, you're a little different. Okay? We don't write little tens next to the numbers we work with. So that's our understood common base that we work in all the time. So to distinguish that from anything else, we need to write the base next to it. All right, so we're going to write base 5 when we have that. How about T00 base 12? So the easy number to find then is actually the succeeding value, that is the number after it. What comes after T00 base 12? T01. Right. What comes before T00? Okay, 9. What's after the 9, Cherish? 999. Because think what would happen. Think what would happen in our number system. What comes after 999? 1,000, right? We take the beginning number, because we've run out of new digits, right? We've run out of digits. So we take the beginning 9 and we increase it 1. Well, what does it look like to increase it 1 in base 12? What comes after 9? Well, we don't need another digit. We don't need a place value, I should say, because we have another digit. We have T. So T would come next. And then the value is 99, just like in our, if we change from 999 to 1,000, all becomes zeros. Okay? You with me on that? A little different thinking, especially if you haven't seen this before at all. So we're going to talk about how we convert. We're going to convert in 2 directions. We're going to convert from our system into base whatever, and we're going to convert from base whatever else into our system. Both conversions, not like we do Roman numerals. Okay? We're going to convert from ours to theirs and theirs to ours. The first conversion we're going to do is from their system into our system. So basically what we're going to start with is we're going to start with a collection of blocks like this. And we're going to count the blocks. So instead of saying that this is one, not pieces, I guess. Instead of saying one block, I'm going to say, well, I don't think this number right here would be 1,000 or 1000 base 3. But what is it in base 10? Well, it's 27. Okay, there's 27 little blocks and I can count them. Okay, so that's what we're going to do, but we're going to do these in 2 different bases, base 2 and base 12. Base 2 is actually a really useful base. Does anybody know things that are done in base 2? Computer stuff, right? Computer stuff is done in base 2. So computer programming. And the reason it's base 2 is because it's a series of ones and zeros, and 1 means on and 0 means off. Ons and offs. And I don't know anything about computers except to know that binary code, which is what this is, binary, base 2, is very important. Okay? So in base 2, here's what we start with. We're going to write our number out. And I like to write placeholders under them. Okay? The first placeholder on the far right-hand side is always the unit. Okay? Which means it's always worth 1 little bitty block. The next placeholder is the long. How much is a long worth in base 2? It's worth 2. Okay, the next one, I know we've got a 0 in it, but let's talk about what it would be. It would be a flat. Well, a flat, like this one, in base 2, would be a 2 by 2, right? So it would be worth how much? 4. So I'm going to write it as 2 squared, just because I'm going to run out of pictures pretty quick here to be able to think about this, but this is the number 4. And then what would a block look like? Well, it'd be 2 by 2 by 2, right? You can see it. It's 3-dimensional, right? How much is 2 by 2 by 2? 8. So this is 2 cubed, because it's the 3rd dimension, and then this would be 8. So the way that we turn this into our numeral is we multiply the value in the place by the value of the place. There is a 1 in the 8th place. There is a 0 in the 4th place. There's a 1 in the 2's place. And there's a 1 in the 1's place. So it looks something like this if you were to write it out. Or you can write powers of 2 in the parentheses instead. I wrote the values of the powers held, but that would be the same. So how many do I have? 11. And if you prefer, you can write base 10 next to it, but if you don't, it's okay because it's base 10, right? It's understood to be base 10 unless you signify otherwise. Okay, is everybody with me? Okay, we're going to do the same process again, but we're going to do it in base 12. So I've got only 3 digits on this particular problem. So I've got the ones place. The next one's the longs. So how many longs are there in base 12? There's 12 attached together in base 12, right? So this is the 12s place. And if I were doing a flat, which is the next one, it would be 12 by 12, which is 144. So I'm going to write this as 12 squared, but you understand that it is 144. Now, the value in each of those places. Well, I have 0 ones. I'm going to work from the right to the left. I have 0 12s in the middle. And on the right-hand side, what does that T mean? 10. So the image you should have in your mind is you have a bunch of flats, right? A whole bunch of them like this. They're big ones because this is base 12. They're all 12 by 12, not like this one. This one's 10 by 10. But you have 10 of these blocks that are each 12 by 12. Can you picture that? That's why I'm multiplying 10 times 12 squared. Because there's 144 here, and I've got 10 of these puppies I'm going to add together. Okay? So I actually have 10 times, and I'll write it in bases this time just so you can see how that would look. 10 times 12 squared plus 0 times 12 to the first, or 12, and then 0 times 1. And I always write the last one as 1 because that just makes more sense to me than seeing it written as 12, 0, even when we're writing in powers of 12. So I really just end up here with 10 times 144, right? Which is how many? Right. 1,440. Are there any questions about this conversion direction?
Without any base?
Yes. Yeah, so if this had been, you can even use the same digits, like this is, if this had 1011 and it was in base 5, that's okay. It just would change all the place values. This would be 1, 5, 5 squared, 5 cubed. And it can be bigger than cubed, I just don't have a physical representation, right? We could have a power of 4. I don't have a good picture of that, right? But you can still imagine all it would do is repeat the process, which means it would have 5 and 4, or 10 to the 4, whatever power we're in. Okay. And now we're going to go the other direction. So we're going to convert base 10, our numbers, into some other system. So the imagery that I always use is this. Imagine I came in, one of these days I'm just going to do it. I'm going to come in and have the big old box of crayons and we're just going to dump them on the floor. And you guys are going to actually do my process. So imagine I come in with this gigantic bag of crayons. Looks like my crayons are going to be, there's going to be 11,028 crayons on the floor. I probably do that real. It needs to be a little bit smaller, I think. But imagine all the crayons on the floor, okay? And what you're going to do is you're going to put them in baggies, little plastic baggies, and they all have powers of 4 values, okay? So we're going to imagine that we have a bag that has 1. These are sort of the leftovers, the ones that don't get put in any gas. We're going to have some bags that have 4 in them. We're going to have some bags that have 4 squared, which looks an awful lot like the number 16 in them. Okay? We're going to have some bags that have 4 cubed in them, which is 64. And I think I'm about to run out of space. Did you know you could do that? Did you guys just see me move those numbers? It's pretty cool. All right, we've got 4 to the 4th. What's that one? Someone with the calculator for me. 4 to the 4th? It is 256, good. And then I have 4 to the 5th. What's 4 to the 5th? 1,024. Oh, I still don't have enough space. We're going to try this one more time. Do it one more time, so do 4 to the 6th. 4,000 something, right?
4,096.
Okay, and just for kicks, I'm going to do 4 to the 7th so I can show you why you don't need it.
16,330.
And why don't I need that one? Oh, all right.
Because it's bigger than
Yeah, it's bigger than the number that I'm working with. The number I'm working with is only 11,000. I don't need a 16,000. Everybody with this part? Okay. Now, I'm going to teach you something that I've never taught before. Your book teaches a different division scaffolding than you've seen, or if you've seen me teach you in contemporary math, I don't teach it this way. And this is pretty cool, okay? But you still have to do everything I did already. Are you with me? So we're going to figure out how many of these we have. So I'm going to need a 7-digit number. Do you see that? 7-digit number when I'm done. And all of my digits are going to be either 0s, 1s, 2s, or 3s. Why? Base 4. Okay. So here's where we're going to start. You're going to start by writing the number that you're dividing by, which is the base you're in, or the placeholder of the base you're in, 4096 on the outside. In the middle, we're going to write the number we're dividing, which is my 11,028. And we're actually going to divide it. So how many times, using your calculators, how many times will 4,096 go into 11,028? More than once, more than twice. Will it go in 3 times? I think it's close, but I don't think it'll work. Yeah. I think it'll go in twice. So if you divide in your calculator, it should tell you 2 point something, right? Or you get 2 point something? All right, here's what I need you to do next. I need you to actually multiply 2 times 4096. What do you get? 8192. Hang on, I put the 2 in the wrong spot for what this method does. So put your 2 on the right. You'll see why in a minute. What did you say it was, Megan? 8192? Yeah, okay. And the next thing you're going to do is you're going to subtract. What's 11,028 minus 8192? 2,000 something. Yeah?
2008.
36 at the end? All right. What we're going to do next is you're going to do the same sort of scaffolding that it had before. Okay? And you're going to do the next placeholder. So we already did 4096. Now we're going to go on to 1024. How many times will 1024 go into 2836? You should be able to look at that and tell me. Twice. Yes. Put it on the right-hand side, and then you need to multiply. What is 2 times 1024? Again, that should be in your head. 2,048. And then we're going to subtract. In your calculator or by yourself, either way. What's 2836 minus 2048? 788. Do you have confirmation from someone else? Sound good? Okay. All right. We're going to do the same thing again. We already did the 1024 spot, so now we're going to do the 256 spot. How many times will 256 go into 788? Yeah, I think it will go in 3 times. So what is 3 times 256? 768. And if I subtract, what do we get? What is it? 20. Okay, so for the sake of my diagram, I'm going to keep going down one at a time on my powers. I did the 256, I'm going to go to 64. Now, I'm going to do the 64, but I realize that 64 does not go into 20, right? Right. Which means it goes in 0 times. But I need that 0 because I don't want to confuse myself when I get back over here and think, well, I don't have 4 digits, I don't have 7 digits, I only had 4 digits or something like that. Well, it's because I got some zeros in there. So I want to represent my zeros properly. So obviously this is still 0, and I've subtracted, and I've got a 20 here. And then I've got, after the 64 spot, I've got the 16 spot. So how many times will 16 go into 20? That one's once. And I would write down 1 times 16, 16. 20 minus 16 is 4. All right. And that's actually my next spot, isn't it? 4. So I've got 4, and it goes in exactly 1 time. And I've got a 4 here. Okay, I've extended my page quite a few times here. Sorry about that. I've got a 0 then left here, right? And very technically, I would divide them by 1. Of course, 1 doesn't go into 0, so it goes in 0 times, and then I'm done. But all of my powers are on the left-hand side represented. I didn't skip any of them. The good news is that if you do it in that way, then your answer is right here. My answer is 2230, 110, base 4. Pretty clean, isn't it? It's a pretty nice way of organizing it. Are there other ways to do it? Absolutely. Like I said, this is the first time I've taught it with this sort of scaffolding method, but I think it works really well. And it works really well to keep you from making some mistakes that are easy to make otherwise. But we should do another one, because I think I've got a base 12 sticking here, don't I? So what's next? Probably. Base 9, oh yeah. So what's wrong with this? I mean, I got 9, 9, 9, 9, and 9. Why am I already in base 9? Base 9 doesn't have any 9s. That's not so good. So I'm going to have to do the same process that I did before. But I need to know how many powers of 9 I've got. So let's see. The first one over here would be 1. And then I've got 9. What is 9 squared? Good. What's 9 cubed? 729. How about 9 to the 4th? What is it? 61 at the end? Okay. Which is still not as big as 99,000. So how about 9 to the 5th? Okay, and you could try one more, but I assure you if you go one more, it's going to be much, much too large, right? So I'm going to end up with a 6-digit number, right? And I'm going to start the same process I did before. So the number that I'm going to be dividing by, which is 59,049, goes on the left. The number that I'm dividing is in the middle, 99,999. And you can tell me at a glance how many times is that going to go in? Once, right? Yeah. And then I'm going to do 59,049 in the middle and subtract. So what is that when I subtract? 40950. Did I get them right? Yeah?
Yes.
Okay, great. And we're going to go down by 1 power. So now I'm going to go to the 6,561 if I wrote it right. How many times will 6561 go into 4950? 40,950. How many times? 6 times? Okay, and then what is 6 times 6561? 366 in the middle? Awesome. And you're going to subtract, right? I think we have less than 1,000 left, don't we? Oh. 1,584. Okay. My next greatest power of 9 was 729. Oops. How many times will that go in? 2. What is 2 times 729? Okay, 1458. And what is 1584 minus 1458? 126. Awesome. Next biggest power of 9 is actually 81. And how many times will 81 go into 126? I said it once. Yep. And then I subtract. What is 126 minus 81? 7. That sounds too big. I haven't put a 5. And then what? 45. All right, that looks good. All right, next biggest power of 9 is 9. How many times will 9 go into 45? 5. And when I multiply this one, actually gives me a remainder of 0. But be careful. You want to make sure you've gone all the way down to 1. So you don't forget anybody. If I go all the way down to 1, I actually get that going in 0 times as well. Okay? So there's my solution, 162150. And I put next to it 9. Any questions? This is one of those things that gets easier with practice. Okay? But what you want to imagine is you want to imagine these base 10 blocks. You want to imagine what happens when you use crayons splayed on our floor. How many bags would I have? Well, what I would have is I would actually have 5 bags of 9 crayons. I would have 1 bag of 729 crayons, 2 bags of, get the numbers right, 2 bags, oh I said right, 1 bag of 81 crayons, 2 bags of 729 crayons, 6 bags of 6,561 crayons, and 1 bag of 59,049 crayons. That's what I would have if I divided these crayons up that way. Okay, that's what I would have if I made little blocks with them, and I could actually represent higher than base power 3. That's what I would have. Okay. All right. So let me pause this.